Sandeep, Sandeep, are you there?
Sir, yes, sir.
I provided a short bio of okay, sir. है ना?
I got it.
Yeah. Good afternoon, sir. Hello. Sandeep,
So,
Sari is joined actually.
but it is not showing the
It is not showing to you. Sandeep, Sari joined
sir.
as a guest. You need to be fined and okay, make him as a panelist.
Sure.
Just you need to check the name. Huh?
So, sir, it's still it is not.
What?
It is not joined.
What did join?
These are the attending list. So inside that total 9 attendees. Finalist
Can
we
you,
are total
can you
11.
share the link? Can you share the link to me on WhatsApp?
Just a second.
Sandeep, can you call to sir?
Just a second, sir. I just forwarded to you. Sir, I sent you on WhatsApp. I sent the link and the panelist password also.
सच सच कर कर किया तो उसको फिर वही रीसेट करना पड़ेगा नहीं जाएगा सेम प्रोसेस
Sir, sir, I think he is not able to join.
तो जाएगा इसमें सर्च करो एक
Sir, am I audible? Sir, am I audible? Hello?
Yeah, you are audible. Okay, Sandeep. Sorry,
Sir,
joined or
sir,
not?
he is not joined. I think he is not able to join. Do one thing, sir. I send one more link on WhatsApp to you. You will just send it. So he will join. He will first register and then join the link. So as a guest, he is able to join, and then I will make as a panelist. So you just forward him whatever WhatsApp message I will take to you. Then
You may check it now. Attendees, na? You may check.
now he is joined, sir. Now just
Hello.
he joined, sir.
Right.
Okay.
Now I can unmute. Okay, thank you.
Yeah.
Yes, sir. Yes, sir.
Good afternoon, sir.
Very good afternoon. Thank you.
We are welcoming you, sir. Thank you very much for it's a pleasure to us.
No. Pleasure is all mine.
Right. Thank you, sir. Thank you. Sir.
Thank you. I'm very sorry for the delay. There was some issue with the host controls not being given and all. Yeah, fine. It is now. It is fine. Okay.
Okay. So I would like to invite Dr. Kondareddy Mahuri. He is the assistant professor at the Department of Artificial Intelligence, IIT Hyderabad. Before joining IIT Hyderabad, Dr. Mokuri was a postdoctoral fellow at School of Informatics, University of Edinburgh, UK. He also obtained his PhD in Deep Learning and Computer Vision from IIC Bangalore. His thesis won the IUPRAI Best Doctoral Dissertation Award and SPCOM Best Doctoral Dissertation Award 2018. He was awarded the Young Alumni Achiever Award for 2022 by his alma mater, the Department of CTS, IISc Bangalore. He received the Faculty Research Excellence Award for 2026 from IIT Hyderabad. His research interests are deep learning, data science, and engineering and computer vision. His work has been published in top tier conference and journal in AI. And Mr. Kondarati recent, he has one good conference, A-star conference, EC 26. So congratulations for sir. That one. He also published two papers in CVPR workshop. And he also published one paper in 2025 in Euro IPS 2025. So this is the complete biography for Dr. Kondarati sir. Now today's session he is taking model reconstruction attack. So now I would like to invite Dr. Kondarati Mokuri. So he is delivering the today guest lecture. So now over to sir.
Thank you. Thank you very much for your kind introduction, and thanks for having me in this wonderful program. So once again,
Thank you, sir, for giving your valuable time for us as well as for all the participants.
no problem. Pleasure. Yes. So can you please let me know if the screen is visible?
Yeah, sir. Your screen is visible.
Right. The slides are moving, right?
Yes. Yes, sir.
Okay. Perfect. So yeah. Today we'll talk about, or we will discuss about extraction attacks in deep neural networks. So there are various names. Different people call the same phenomena with different names. So I intend to call these attacks or these phenomena data-free knowledge extraction. We will see why we call this is data-free knowledge extraction from deep neural networks. By the way, you can stop me at any point in time because my screen is showing my slides. It may be difficult for me to see the hands that are raised. So you please unmute yourself, and I will stop and listen to your question. If you have any question, you can do that. It is okay. Okay. Please don't wait until the end of the talk, or don't wait until the break. Okay. I'll be happy if you can stop me and ask the question. All right. So today this is what I will cover. I'll first introduce what is data-free knowledge extraction, how I kind of moved or explored in this direction. I'll talk about uh, three different ways of doing data-free knowledge extraction. In the literature, I will show. I'll group the bunch of works into three categories. So the first one is noise optimization for data-free knowledge extraction. The second one is generative reconstruction for the same phenomena, and third one is data-free attacks. Basically, what sort of things are happening may happen in the foundational models era. Okay, but slowly we will build the understanding. We'll try to understand the depth of the matter, which is the security. That is the theme of the this program. So let's try understanding the basics. Okay, so how it all started in my case. So deep learning is a success story now, right? Everybody understands the potential of deep learning. It may be, it may not be incorrect to say most of the state of the art systems in AI are driven by deep learning today, right? It may be true, okay? How do we know? Because we've seen numerous applications and impressive performances across the domains, across computer vision, speech processing, natural language processing, and it cuts through different verticals: manufacturing, finance, automotives, banking, everywhere, healthcare, right? So it is so vast. The success of deep learning is very easily felt in our day-to-day life, in the form of applications that we are using, the tools we are using, right? But when it comes to the deployment of these models, let's say you have successfully developed a new architecture, very capable of doing things. When it comes to deployment, predominantly there are two things that are possible. One, you hand over the model, right? You, being a researcher in deep learning, you develop this thing in your lab or the cloud, and then to the customer, you deploy it. You give it physically, saying that this is the model. Okay. Now the the customer can take it and install it in their products. For example, think of an application in a mobile. Think of an application in a car or a truck, right? So that is possible. You hand over the model and it can be installed in an environment. The second way to deploy things is basically deploying it in a cloud and allowing access to it on a pay per query basis, right? Because there may be sophisticated models that require a lot of compute, lot of memory. Not all handheld devices may be able to host it, right? The battery requirement and the memory requirement may uh, hinder it from deploying it in handheld devices. In that case, what you do, you deploy it in the cloud and you ask the customers to pay as and when they use. That is why we call it pay per query, sort of. So what happens? The user gives in the input X, and the model, which is in the cloud, performs the inference and provides f of x. So you need a high speed connectivity like 4G, 5G, 6G in this scenario to perform the query and the inference. Okay. Now let's look at the first case, handing over the model physically. Okay, so we'll talk about the security aspects surrounding this deployment modality. Okay, we will go to the second modality also after analyzing the first modality. It is not, it is very common, right? See, some of the models, some of the devices that we are using, including cars, laptops, mobile phones, tablets, they may have deep neural networks trained to perform different tasks, face recognition, etc. Right? Biometrics, etc. Maybe other sophisticated applications like object recognition, etc., are also possible to be deployed on the handheld devices. Now, let's say what I'm going to claim here is that you have a model which is trained on some training data which you don't know, which you don't have access to. So that's why I say you have a model, but the training data is not there with you, because this is very common, right? We may have the trained models without the training data. It's very common. You may think, okay, what are the reasons why the data is not provided? Because it is easy to understand, data is the new oil, right? Nobody wants to lose the data, because data, if you properly learn from it, it will create wonderful models. So nobody would like to give away the model, the data. Rather, they can sell the model that is trained on the data, right? Another reason can be privacy. They are not supposed to give away the data. They have some policies that bind the data, distribution of the data, right? But they can train the models without losing the privacy of the candidates. Because of that, they may not be able to give away the data. In some experiments, in AI experiments, for example, where RL is involved, the training data is dynamic in nature. Right? Training data is what the agent interacts with the environment and the state of the environment. Sometimes it can be simulated. Sometimes it is difficult to recreate all that training environment. So it is impossible for us to share the training data. And the fourth reason can be, it can be huge. It can be GBs and TBs. It's not easy to share the model. On the other hand, share the data. On the other hand, the model can be relatively easy to share, right? It can be Even the big models can be of a couple of GBs maybe, right? Even the big ones I'm talking about, right? So that is relatively easy than sharing the training data. So there are all these kind of reasons why you can expect a model to be shared or purchased, but not the training data. Now, in this case, models in the training data, what can they do? We all know models which are already trained, they can be used to perform inference. That means because you purchased it, you can use it for deploying. That is what the deployment scenario we are talking about, right? Somebody trained and gave it to you. You can use them for pre-training also. For example, you want to build another system, you want to build another, machine learning model, but you can use this as a pre-training, right? As a transfer learning, you can carry forward this models learning. This is all possible without the training data. But what is not possible when the training data is not available to you? People thought it is not possible for us to do model compression or data knowledge distillation. Also, they thought fine tuning to add more classes or to add more data belonging to the same classes. Also, continual learning, adding more classes, more abilities, more tasks may not be possible, because if you add more tasks and start training on it, the old tasks will be forgotten. This is called catastrophic forgetting. The parameters will change because you are adding new tasks, new classes. Because of that, the old data, old tasks will be forgotten. That's an observed problem. So people thought without the training data of the previous tasks, we don't venture into continual learning and fine tuning, right? Yeah, adaptation also is not possible, because if you adapt so much, the old tasks will be forgotten because you don't have the data to retain the ability of the model on the old tasks. Okay, so these are generally what people thought. I'll spend a little more time on knowledge distillation. So I said people believed that knowledge distillation may not be possible when the training data is not there. Okay, but that is where people, particularly our group, when I was in IASC, so we thought about this for a while and asked this question: why can't we do knowledge distillation when the training data was not there? Okay. Now, what is knowledge distillation? I'm sure some of you may be aware of this thing, but for the completeness sake, I will spend a minute or two on knowledge distillation. As the name suggests, we are trying to distill the knowledge of one model onto another model. Okay, why do we do that? There is a high capacity model which has enough capacity to learn on big data sets. But because it is large, it cannot be easily deployed on resource restricted environments like handheld devices where battery, memory, latency, everything matters, right? So that is why what people try to do, they try to compress the model. So that is where knowledge distillation came into picture. They used knowledge distillation to train smaller models that try to do as well as the bigger model, high capacity model. So generally the high capacity model is called teacher and the low capacity model is called student. Okay, so this is how you have to imagine. There is a big data set over which we trained a very big model where performance was only criterion. We did not worry about the overhead, memory overhead, latency overhead, nothing. We just wanted the best performance. So in the laboratory, we trained a big neural network. But as I said, this cannot be easily deployed. So we need something lightweight to be deployed, but the lightweight means lesser capacity. If you train this model on the same training data, it may not perform as well as the bigger model. Now, how do we train the smaller model to do as well as the bigger model? That is where the distillation comes into picture. Okay, so this is very useful in model compression, as I said. What do we do in knowledge distillation? This is the teacher. T stands for teacher. It is trained on the big data set, which is supervised for the time being. Let us assume this is a simple object recognition sort of task where each image X has a label Y. Okay, it is already fully trained and you are happy with the performance, but you are only not happy with the size, the latency, the memory requirements, and battery requirements. So that is where you introduce a lightweight student Now you try to perform distillation from teacher to student. What do we mean by that? Whatever is the teacher predicting, you want to just imitate that by your student. Okay, because this teacher is trained, it will do good job of predicting the labels or the soft labels, which is basically predicting the probability for each class. So you want your student to imitate the teacher. Okay, so you minimize the distance between the teacher's output and the student output. Okay, so because the teacher is doing good job, you encourage the student also to just imitate. And because this is a supervised setting, you can also have a cross entropy loss, the typical way we train a classifier. Okay, this is also there, but more weightage is on imitating the teacher. You do this for all the training data. So this loss will train the parameters of S. Remember, T is already trained independently and frozen. These parameters are not going to change. We are happy with the teacher performance. All that we are trying to do is that encouraging yes, the student to imitate the teacher. This is very powerful objective, and people have used this very well to compress such models. So if you do this, and by the end of this training, the student will do better than its capacity because it is trying to imitate the teacher. Okay, it's not a magic if you really understand what is happening here. It is just trying to do what teacher is trying to do. Beyond its capacity, it will be able to perform because there is more input coming from teacher. I'll show you what is that input coming from the teacher. Okay, so this is a typical deep neural network classifier. You'll have an image input and there are multiple layers, and towards the end you will have confidences predicted for each class, which after applying softmax will become a probability. For this case, this is a truck. So the model, a well-trained deep neural network, is predicting 0.69 probability for truck class, 0.30 for car class, and 0.01 for a carrot class. It is reasonable, right? But the hard label, human annotated label, is 100. It simply says it is a truck, right? It assigns no probability for other classes, full probability for the truck. So the hard labels has very limited information compared to the soft labels. What does the soft label say? The input is 69% truck, 30% car, and 1% carrot. So clearly there are certain features that are shared between these two classes, car and truck, right? The wheels and the windows and certain other parts of these overlap, right? That is why you have non-zero probability, non-trivial probability for the car class, which was not there in the hard labels. If you use them for training the student, it will certainly not do as well as training on these labels. How are these coming? These are coming from the teacher. So this will help the student do better job. Try to understand it is a truck, but it also bears similarity with car. It has no similarity, almost no similarity to carrot. So this extra information is very important. Okay, this is called latent knowledge. It was not there provided through the hard labels. Only the distillation framework is bringing this out. Remember? So this is where I'm talking about the teacher's output of the input. This is the softmax vector. This is not a hard label. Instead, it is a soft label like this. This and whatever student is predicting, we will try to match these two. So the student is forced to follow the teacher. So that is where this latent knowledge given by the teacher will help the student do better than its capacity, right? So this process is called knowledge distillation. People have, as I said, this finds a lot of applications in compression actually. Multiple works, multiple deployments benefited from distillation. Okay, so this is the key. If you are wondering how will such a low capacity student will try to do as well as teacher, remember it may not match the full capacity of the full performance of the teacher, but it will try to do better than its capacity and try to match the teacher as much as possible. Okay, it also depends on how small is the student when compared to the teacher, right? Generally, it will be an order less magnitude, right? At least an order. It can be even more compressed, 10 times, 100 times compressed model also. Okay. So this is the key. We try to make the teacher output as uh, less peaky as possible, right? You need this latent information about each input to feed into the student, right? That is where they use this trick called softmax with temperature. What it essentially means is that you try to make the peaky softmaxes less peaky. For example, you look at this, 97% of probability is there on one label, and the 3% is shared among the other three, right? It is very peaky. It may not be very useful. It is close to hard label, right? We don't want that. So if you use a temperature in the softmax which is dividing it by t, the gap between these will be reduced, and the probabilities will look very close. Now let's see, 97 becomes 30, 1 becomes 23, 0 becomes 22, etc., etc. So the output is less picky now. Now you know the intra-class similarity. Sorry, inter-class similarities are very strongly captured here. This information is vital. This is all the latent knowledge. Okay. Again, so this is the knowledge distillation. Now, where is the? There are many ways to do knowledge distillation. It may not be really important for us to understand the attack, the security side of it. So I'm skipping this 1 2 slides. It is not really important. Okay. Now, what is required in all this business? The training data is required. If you see, once again, without the training data, you cannot perform knowledge distillation. Okay, it requires training data. Once again, let me show the objective. We were using the X, which is the training data, to pass through the teacher, and the same X will pass through the student. And whatever teacher is predicting, I want my student also to predict the same thing. But if I remove X from this framework, you cannot run the knowledge distillation. That is why people believe that knowledge distillation requires the training data on which the teacher is trained. Now come back to the setting where we were. We were in the setting number 1, where somebody trained the model and gave the model to you, which is very well trained without the training data. Now, what can happen to that model is what we are worried about. Okay. Now, this question is what I'm going to ask. Can the trained teacher model help us with this set to transfer the knowledge? Because it is helping us to transfer the knowledge from the teacher to student. Generally, we refer to this as transfer set, because the whole point of this data set in this job is to transfer the knowledge from teacher to student. Can we ask the teacher itself to provide us the knowledge, the transfer set? Yes. So that is where the very first work from our team came back in 2019, was published in ICML, Machine Learning Conference, International Conference on Machine Learning. We even developed it to other applications, and then got published in PAMI, Pattern Analysis and Machine Intelligence, a couple of years later. These works are well received. So how do we extract the patterns or the transfer set from the teacher itself? Remember, this is what we are given. Somebody trained the model. You can think of it as a simple image classifier. Let's say it's a VGG or ResNet trained on ImageNet. ImageNet is 1.2 million images, maybe close to 200 GB if you download all of that. But this model is only 220 MB, very small compared to the full ImageNet data, 1.2 million images. Right? Now, what we are trying to do is that can we get the patterns of the training data? Patterns means the visual patterns, how the objects in the data set looked. Can we extract those patterns from the parameters itself? Remember, I mean, we don't know what are the images, right? We only know the parameters of the model. Now I want you to see the security aspect here. Somebody is trying to look at the data patterns. Somebody is trying to look at the image contents over which the model is trained. So there is this security aspect. Okay. But the interest started with how can I transfer the knowledge from this teacher when the training data is not available. Okay, let's say these are the classes, right? There are 1,000 classes in ImageNet. So let's say you are worried about Lakeland Terrier, one of the classes. It's a dog category. It's a dog breed, Lakeland Terrier. Okay. Now, if this is what I want to see, what kind of images belonging to this class were there in the training data? This is my worry. Okay, how do I do that? I will randomly initialize an image. This is just a noise, right? Think of this as a canvas, empty canvas. Just randomly initialize a noise. Now I want to see what patterns on this image will increase the confidence for this class. When I pass this through this trained model, what patterns should be here so that the confidence predicted by the model for this class is more. Okay, so this is the question. It's a very interesting question. So we do a simple gradient ascent uh, algorithm, gradient ascent iterations to increase the confidence of the model for a particular class. Initially, when I pass this through the trained image, it will almost give zero confidence, zero probability for this class because it doesn't look like a dog. But I will try to change these pixels in order to increase the confidence for this class. That is what the optimization here does. Argument X that maximizes the model's confidence to a particular class C. Okay, so this we were trying to do something else in our ECCV 2018 work, and this is where it all started for us. How can we extract the patterns from the trained parameters? Is it possible for us to extract from a deep neural network classifier what patterns were there in the training data? Now, this is what we achieved. After hundreds of iterations, these patterns evolved. Remember, this I won't say it is a magic, but it is nice result because from almost nothing, we could extract the major or the dominant pattern belonging to that class. And this can happen to any class, any of the 1,000 classes. You could extract patterns from goldfish, wolf, spider, Lakeland Terrier, monarch, whatever it is. These are only a handful of images. You refer to this paper, we have in the supplementary many more such results, right? So these we called class impressions because these are the impressions model carried from the training data, and we could extract these with only access to the parameters, nothing more. No training data we were looking at, only the trained model. We did it for all the popular classifiers like VGG, ResNet, etc., etc. Okay. Now this is where we started. Can we use these images to transfer? Remember, it all goes back to performing knowledge distillation without the training data. Now we have some patterns extracted from T. Can we use them in place of original training data and train my S to do as good as T? Okay, so that is the problem. We used these class impressions and we transferred the knowledge of teacher onto the student. We generated samples, but they are less faithful and less diverse because we could only extract the dominant portion, dominant pattern, belonging to each class. The result wasn't very diverse, right? For example, each class in ImageNet has about 1,200 images. Each class has a training data of 1,200 images, but we could not generate 1,200 diverse samples for each class because only the dominant pattern that belongs to each class could only be extracted through this simple optimization process. Okay. Also remember one hot vector label. What did we do? We increased the confidence for this. What is the result? All the probability goes here, which becomes 1 and all other zeros, right? 1 and all other zeros. When will we stop? When the confidence predicted becomes very close to 1, that is when we stop. Okay, so that is why we say one hot vector labels are reconstructed. So we are reconstructing the input which will predict a one hot vector. Okay, but that may not be very correct, right? Because one hot vector means minimal latent knowledge, minimal dark knowledge, not so close to the natural data, right? A trained model will never give close to a one hot vector, right? it typically gives non-binary predictions, right? This is what typically it gives. If you use temperature, it will give something like this. But we are optimizing for a binary or one hot vector encoding. So that is why we observed, although there is promise, this is not going to give us representative patterns, more and more variety when we reconstruct every time. No, every time we reconstruct, it was going to be the same pattern, but located somewhere from top left to bottom right. The location of the pattern was going to change, but diversity was very minimal. So that is where we thought about, because if there is no diversity, obviously when you perform knowledge distillation, the student will not be able to generalize very well. You only have very small variety in the training data. Here the training data means to transfer the knowledge from teachers to the student. Okay, so this is where we took out this problem. We need to improve the modeling of the output space. Okay, that is where we came up with this first word, ICML 2019, wherein we modeled the output space. Output is a softmax probability, right? It will be a probability vector, PMF, probability mass function over the 1,000 classes, if it is ImageNet. If it is CFAR 100, it will be 100 classes. Okay, so how can we make the output vectors reliable? Reliable in the sense reasonably practical. Okay, as I said, all zeros but one is not a practical output for a trained neural network, right? So we need to find what we should reconstruct. Okay, that is where we model the output space as a Dirichlet distribution. Dirichlet is a probability distribution over PMFs. Okay, so it's a bit involved. Please follow me, and if you have any questions, you can stop me. So the support for this probability distribution is k-way classification probabilities. Okay, so each of the sample from this distribution is an output of k-way classification. Okay, so we want to model the probability distribution over probability distributions. Okay, so this is how it looks like in 3-class scenario. The parameter alpha is what manipulates the mass. All these regions are probable, but which regions are more probable depends on the alpha. Alpha is the Dirichlet parameter. So for example, if you have equal for three-way classification, if alpha is, it's also a three-dimensional vector. If it is equal, all three will have similar probability, but these innermost regions will have a more probability because of the values being very small. If the values are large, it will go towards the vertices of the simplex. Okay, again, you don't need to worry too much about all of this. Essentially, we are modeling the output space. Not all probabilities are equally likely, particularly the one hot vectors are not very likely. So we went ahead, analyzed the trained model because the parameters are available to us. We could understand what are the interclass similarities. I want to understand how class 1 is similar to 2, 3, 4, 5. And I want to understand class 2 is similar to other classes because some of them are dogs, dog breeds. So among the dog breeds, the similarity will be high. Among others, it is not very similar, right? So interclass similarities is what we wanted to capture, and based on that we want to understand some softmax vectors are more likely, some softmax vectors are less likely. Okay, so definitely one hot vectors are not so likely. So that simple observation helped us to model this confusion matrix. Now because there is a template, right, in the trained model, this is a CNN that is trained to classify images of ILSVRC or ImageNet. Okay, so these parameters are trained and given to you. That is what the situation one was. Somebody trained the model and gave it to you. All the parameters are very well known. You know the architecture and the parameters are there with you. Okay, so look at the last layer. Last layer, this is the feature. It will be dot product with the first W1 to get the confidence of class 1. There will be W2 for second class. The same vector output feature will be taken as dot product with W2, will give the confidence to the second class, and so on, W3, W4, W5. W1 is a vector which connects this feature to the first class. W2 is a vector which connects all these neurons, one output feature with the second class, etc., etc. So W1 is template for class 1. That is when the output feature is similar to W1, this will be high. When this feature is not similar to W1, the confidence will not be high. Right? So essentially W1 is how class 1 looks like. If the feature is close to W1, similar to W1, you will have the confidence high for that W1, right? So that is the key observation we made. And we look at these vectors connecting the output feature to the classifier confidence as the templates, class templates. So now you have one template for each class, W1, W2, W3, and so on, WN. Now we can take a dot product and understand which templates are close by, which templates are not close by. So this normalized dot product will help us get the interclass similarity matrix. We call this class similarity matrix. And any row you see, plane, how similar it is to plane, car, bird, etc. Okay. So whenever there is a strong value, this class is similar to that class. Wherever there is no strong value, we say those classes are dissimilar. Okay, so according to this class similarity only, softmax should be there, right? Not every arbitrary softmax vector makes sense, right? You cannot have a softmax where plane has good probability and horse also has good probability. It is very unlikely, right? Because plane class will not share similarity with horse class. On the other hand, the ship and the plane may have similarity because both of them have blue backgrounds. Ship often has blue background because water looks blue, and plane also sometimes have uh, plain blue background. When it is flying in the air, a photograph will have a good portion of it blue color, right? So that is why you see plane sharing good similarity with ship. So this color, greenish color, which is somewhere here, is not close to zero, right? It is non-zero. And similarly, car shares similarity with truck, right? You can see car and the truck. Similarly, car, truck. So there are some patterns which enable us to understand what classes share similarity, what classes do not share similarity. This is the information we stole from the given model parameters. Now with this information, we can reconstruct a meaningful softmax, not a one hot vector softmax. In the same way, the data impressions are class impressions. When we reconstruct using the gradient ascent mechanism, we don't need to look for any arbitrary or one hot vector softmax soft label. Instead, we can sample, we can model the Dirichlet distribution on the class specific softmax vectors. That will give us what is a reasonable softmax for each class, plane class, car class, etc. So this is a very simple but very clever thought. We felt it will give us better modeling of the output space so that we could reconstruct better the patterns. Okay, so we did this. We replaced the hard labels with soft labels we constructed through this Dirichlet distribution, and then used them as a transfer set. Okay, because this transfer set has soft labels, we wanted to work with only distillation loss. These are not hard labels, right? You will have soft labels now for each of these samples that we reconstructed from the trained model. With this, we show very non-trivial results with the reconstructed data. Remember, these are not original data. That is why they don't look like real samples. But you have patterns. There is a bird here, you can see. There is a car, wheels are there, right? So these are all model patterns stolen from the parameters in a very tricky way, in a very clever way. And we used it to transfer the knowledge of teacher to the student. And it does very well actually. It does. This is called zero shot knowledge distillation because we are not using any training data. When you are not using training data, it is called zero shot, right? So this we showed on multiple benchmark data sets like MNIST, CPAR. It is coming. It won't do as good as the full training data, but that's okay. It is doing very non-trivial data. For example, a fully trained teacher on CPAR 10 will give 83, and a fully trained student will give 80. And With all the training data available, the same student will do 80.08, and without any training data, we do only about 70. So 10% close to a fully training data student. Okay, this is a proof of concept, and we did this for many models like VGG, ResNet, different variations of ResNet and VGG also. And we showed the most important thing is that without the training data being made available, you can transfer the knowledge of the teacher onto another student model. Okay, that is a little troublesome also, because as I said, you purchased a car, there is some very sophisticated deep neural network model deployed in that. Now you quickly perform this kind of knowledge distillation, you will have a duplicate model which does not perform as well, but which tries to perform as well. Okay, so without the training data, because the corporation which trained that model may not give you training data, but you say fine, I am fine with data free environment, I can just take out this model and do my magic, create a an emulated version of that. Right now you can probably create a business out of this secondary model. Okay, so that is the danger we kind of see. We saw that the approach is making the big inquiry whether it is possible to transfer the knowledge of the teacher without the training data. Okay, so that is where this it all started. That is what has opened the doors for knowledge distillation, knowledge extraction, model stealing, model extraction. You call different names. Essentially it is transferring the knowledge or extracting the knowledge from one model to another model without the training data access. Okay, so such works which followed our work later, all of them are called noise optimization, because we are using noise and optimization to prepare or to extract the patterns for the purpose of creating another duplicate or replicate model. Okay, so it's as well as stealing the model, right? Somebody has given you, you purchased it, but you quickly produced another duplicate, right? Okay, so this is the first thing that we are going to talk about for today, noise optimization. How can we start with noise and use optimization to prepare or to steal patterns from the training data? Okay, so essentially three steps. You start with the noise, you can start sampling a Gaussian distribution, then perform iterative gradient ascent. As I showed, right, in the figure, there was a noise on the left and there was one class you picked and you try to maximize the confidence for that class, argmax of x, which maximizes the confidence for the selected class. You do this for every class one at a time, you have patterns for all the classes. Okay, once you have that, you perform knowledge distillation. You will have the student which tries to perform as well as the teacher. I'm not saying it will perform very close to, but given a data free scenario, this is the best you can do. Okay, right. So this is the optimization. Different papers, different works came up with uh, better and better optimization techniques. For example, you can have a regularization while you try to maximize the confidence for one class. You can also try to have uh, some natural image statistics based prior. For example, this can be to make the output smoother, right? Because natural images will have very smooth patterns, right? Most of the region will be smooth regions, only edges will be there in sparse quantity, right? So if you can mathematically put all those intuitions into a regularization, it will look closer to an image, so that more knowledge can be transferred from teacher to student. If you have more insights, for example, I'll show some suitable regularizations people have tried over time. So one of them tried to maximize the similarity to activations that were saved. For example, when I pass my synthetic data, so I'm calling it synthetic data because this is not real data. We reconstructed the data. So for that reason, I'm calling it synthetic data. So what I can do, I can save the real data statistics. Let's say after layer one, how the features looked when the real data was passed. how the features of second layer, third layer, etc. looked when the real data was passed. Now I will try to get the similar statistics, similar features when my synthetic data also passed, right? So I can have such a regularization so that the synthetic data becomes closer to the real data, because there is another regularization binding it to be closer to the real data. Okay, that is what regularization does, right? It regularizes your training. It will control and smooth out the desired properties into the training, into the output. Okay, so this is not really data free because you are storing the statistics of the real data, not the real data, but statistics. What do I mean by statistics? The mean of the features at different layers, the variance of the features at different layers, etc. Okay, so that can be your regularization. Mean and variance you can store, and you try to match when the synthetic data is passed. You try to match the statistics that are that to be close. This is real, green one, and the red one is synthetic. So when you pass the synthetic features, you can force them to be closer to real. That way you are forcing the synthetic data to be closer to the real data. Okay, this is all clever regularization to make the patterns more and more real looking, more and more close to the training data. Okay, all right, so it is not data free completely, but metadata is saved. Okay, another observation is activations cannot represent the complex training data. Activation is what? One statistic, right? It will have various patterns, a variety, diversity is not really captured. So it cannot be applied to sophisticated models like ILS VRC, where bigger images, complex data set, strong variety is present, right? But you can think of classes like face classes, models that are trained on only face images, or something, a scenario where the diversity may not be very much. That kind of a scenario, they still work. Okay, so essentially, noise optimization with a clever regularization can help extract features, patterns from the real data and use it for creating replicate models. Okay, so for example, Deep Dream 2015, this is very popular. You might have come across this also. They used a regularizer which is total variation regularizer, which is essentially another way to say real images will have smoother regions, dominantly smoother regions. So you can have within a neighborhood, you can have within a neighborhood, you can have pixel values to be very close by, or you can have gradient within a neighborhood to be very, very close by, right? Things like that. Okay, so with that kind of regularization, you can see the patterns are getting closer to real data. And even more closer to real data happened in 2020, deep inversion. What they did is, by then, batch normalization layer was very common in convolutional neural networks. So they used those statistics because batch normalization will have a mu and sigma parameter, which is basically statistics of real data at that layer. So that is very, very useful. We could replicate those mu and sigma, right? And with that, you see what is possible to extract from trained neural networks. These are synthetic images extracted from the trained models with batch normalization layer. Okay, so these are not very bad. I'm sure these are not real. It is easy to say that, but look at the patterns. Look at the training data patterns that are extracted. Right? Think of a healthcare scenario, healthcare context where the models are trained on patient's data, and you are reconstructing that data, including, let's say, sensitive attributes like gender, age, um, other things like region, right? So these are very, very sensitive, and this kind of tells that models may leak out all that information if you ask them in a proper channel, right? So this deep inversion results are very impressive. Okay, so let me quickly summarize all this bunch of works called noise optimization. They require hundreds of gradient ascent steps, right? It won't happen that noise to this conversion will not happen instantaneously. You have to do hundreds, sometimes thousands of iterations. Then the canvas slowly moves from noise to one of these patterns, right? It requires that many iterations. Every sample you have to do that. It's very costly, computationally expensive. But then you're trying to do extract information from parameters, it is costly. And quality of the alternate data set can't be determined using synthesis. Okay, what it means by that is, so this data set we are creating for transferring the knowledge, it cannot be understood during the synthesis itself. You have to put it in action by training a model. Only then you will understand how good is this synthesis. That is one sort of a important thing. If it is useless, how do you find? Only if you train a neural network on top of that. At that point in time, you will know. If it is really useless, all this effort goes waste, right? So this is one observation people had. It's easy to see you are synthesizing and then you have to take it somewhere, right? So that is why it may not be useful. Okay, so that's about the first option, the first branch, which is noise optimization. Okay, so I'll quickly pause. If you have any questions, please let me know. We will go to the other two I wanted to discuss. Let me see if there are any questions. Right. For some reason, I'm not able to see where I am. Okay, here. Right. So if you have any questions, you can put it in the chat box. All right, good. So it's good that everything is going smooth. So let's quickly take 3 minutes break. It's 4:27 now. Okay, you can just stretch out, get up from the chair, have some water or tea, coffee. But 4:30 we will resume. I hope it is okay. Just 3 minutes break. Okay.
You will take and then come back.
3 minutes.
You have make a replacement.
Right. Because continuing for 2 hours may not be a good idea. So we will take a quick pause. 3 minutes, we'll come back. Okay.
Sure.
Thank you. All right, so let's resume with the second and third. The second one, I want the approach to perform knowledge extraction or model steering is generative reconstruction. It's an adversarial framework. We will see what it is. So for that, we need a little background from GANs about the generative adversarial networks. So these are very popular generative models. They can draw high quality samples from underlying data distributions, right? We don't know, for example, generally what is the starting point. We have lot of training data and we want to train a GAN which can draw or which can generate similar samples, not exactly the same thing but very close to, right? That is what we mean by drawing samples from the underlying distribution, but we don't have that information. We don't know what is that underlying distribution. All that we have is the samples. Okay, so without actually computing the densities, p model or px, p data, the GAN ensures the closeness of the samples to the training data, right? So this is what GAN was, right? So you have a lot of training data. The GAN will have a generator part and the discriminator part. It will sample a simple data distribution, simple distribution. It can be a N0I uh, Gaussian distribution in some lower dimensions like 50, 10 dimensions, whereas your samples are in high dimensions. These are RGB images, high quality, 512, 512, 1024, 1024, very high dimensions. So this architecture pair, generator and discriminator, they play an adversarial game wherein the generator tries to come up with fake images, but the discriminator tries to understand whether this is fake or real. So in this game, the generator will build skills to develop models, generate models that are close to real data. That is where the discriminator believes these are also close to real data. That is when we say the training is done, the generator is good. These samples can be believed to be the real images. Okay, I'm quickly summarizing. I'm sure GAN is a very popular generative model. You may be aware of. Just for the sake of completeness, I'm doing this. So this is the objective. So for all the real data, discriminator gives high probability to be real. For all the fake data, Z sample from PC, this will give, the discriminator will give very poor probability. But at the same time, generator should give more probability. Okay, that is why the generator will try to minimize this, but the discriminator will try to maximize this. Okay, this is why we say this min-max game or adversarial game between the generator and discriminator. Okay? Think of this as a very, in crude terms, think of this as a um, of counterfeit note generation and law enforcement. Okay, somewhere the counterfeit note generation has to be very close to real so that the discriminator, that the law enforcement feels confused and they accept. Okay, so that is what happens in GAN. Okay, so now how do we use GANs for knowledge free distillation? So noise optimization, which we have seen, enforces prior about the training data. What is the prior? Total variation, smoothness, sort of prior, right? Or batch norm statistics, that is also another prior. Can GANs also do this? I want the GANs to work with the trained teacher, extract the patterns that are present in the training data, but we don't have access to the training data. Okay, that is the problem. Can the GAN synthesize samples that reflect the training distribution via this so-called smart regularization? Okay, I'll show you how. So it can be activations, it can be predictions, it can be batch norm statistics. Okay, so it can be anything. Can I also use this in the GAN setting to bring the patterns of the training data from a trained teacher? So this process is called generative reconstruction. Okay, so we reconstructed using noise optimization in the first bunch of works. In the second, we use GANs. Okay, so this is what GAN does, right? Sample the simple noise distribution, pass it through generator, you will get fake image. X tilde is fake image, and then that goes through GZ, the fake image goes through a regularizer and the teacher. Okay, this fake image should be very close to, it should generate very close to the batch norm statistics. That can be one regularizer, right? So you can be creative. I want the generator to understand what I am looking for. I am looking for those patterns that are similar to the training data. All the cleverness, intelligence comes here. How can I mathematically tell the model what it should extract? So that is where in noise optimization we used batch norm statistics, metadata, if at all we saved any, or the general image priors. Natural images will have smooth regions mostly. So you tell all of this prior knowledge into the system with mathematical regularizations. Okay, so that is the key. So that is where I want you to understand how it goes into the system, how this knowledge or cleverness goes into the system is this way. Regularization to take care of the fake data and the teacher. We want to extract patterns from this specific teacher, right? With that in the picture, you need to apply the regularization. Okay, so alternate between synthesis and distillation, because you are trying to synthesize the data and also try to use it for the distillation or transfer. You need to train the student simultaneously. Remember, one of the drawbacks in the noise optimization is you don't know the quality of the synthetic data until you train the next student. You generate first and then take it to student training, but it is too costly and time taking. That is where generative reconstruction comes and also simultaneously synthesizes and distills. I'll show you how it happens. I'll show you. So the first work happened sometime in 2019. DAFL, it proposed three terms to regularize the generative reconstruction. Okay, so what it does is, let's say this is my random signal. I am passing through the generator. It is giving me a fake image. Now that I will pass through a trained teacher. Remember, we have a teacher given to us, trained, but no training data. That is the blue one, the big teacher. Now this orange one is smaller, lightweight student, which I am trying to create to act as a replica of the teacher, right? So I'm trying to create a replica of the teacher in this orange one, where I don't have the training data. Okay, so this is where I will start from random signal, create some fake image. Now I will pass the same image to both teacher and student. I want them to match. Okay. At the same time, I want this data to behave in a specific way. How the cross entropy between the teacher's output and the label should be minimum. Let's say I am trying to extract patterns belonging to one class, which is cat. So the cross entropy loss between the output of the teacher and the one hot vector encoding of the cat should be small. That is when this looks like a cat, right? Because it has to be believed by a teacher which is trained as a cat. When will it happen? When it actually has a cat, it will believe that as a cat, right? So this regularization, one part of the regularization is to pass it through the teacher and reduce the cross entropy loss for the chosen class. And the second one is, if this looks familiar, more activations will happen in the teacher, right? So that is what happens, right? This is called in distribution data. When the teacher is trained on, let's say, RGB images, and now you input some medical imaging X-ray data, it is out of distribution, right? The model will not fire, the neurons in the model will not fire in good number because the distribution is different. So one way to make this synthetic data close to the real data or the training data is make sure there are enough activations in the training, in the teacher side. Make sure there are enough activations. What do I mean by activations? The layer outputs being very strong, right? L1 norm or L2 norm should be very strong. The negative of it can be minimum. That means the norm of the activations is maximum, strong, right? Another thing is that the entropy of the teacher output should be minimum. That means you need to have a peaky output. That means the teacher's confidence is high. When will the confidence be high? when it is coming closer to the real data, the training data. Okay, so very carefully, these multiple terms in the regularization will help the generator to pick the samples or to paint the patterns of the training data on the canvas. Okay, again, I will repeat it. Because of all these conditions, forcing the generator to understand what can excite the activations in the teacher, it will only try to paint those patterns that are familiar to teacher. What are those? Which were present in the training data, which is not given to us. Despite not giving, we are able to encourage the generator to catch them. Okay, so in a very crude terminology, we are trying to steal those patterns from the teacher parameters by intelligently crafting the regularizations. Okay, so this is a very successful framework. From 2019 onwards, next 4-5 years, maybe people exploited this generative framework called generative reconstruction to steal the generator, the patterns of the training data, and simultaneously train the student network. Simultaneously, they are training student network as and when they are, you know, generating or training the generator part. There is no discriminator. You see, this is a very tricky part. The generator of the GAN is there, but there is no discriminator. There is a student network which is a classifier similar to the teacher network. That itself, the interplay between these two should be acting as a discriminator. Okay, I hope I clearly conveyed the framework of generative reconstruction. So when you perform this training, slowly the teacher gets the generator gets the ability to generate patterns of training data over which the teacher is trained, and simultaneously it keeps training the student. You don't need to wait for training the generator first and then training the student. Simultaneously, generator and student, both of them get trained. Okay, so this a bunch of works, as I said, all of them use different regularizers that I just described. They distill multiple teachers also. Simultaneously, you can have, if you have multiple teachers, all of them can be incorporated here. All the knowledge of multiple teachers can go into the student. Okay, so without the training data, you are just squeezing the knowledge of multiple teachers onto a student. Okay, so people have conducted multiple such experiments and showed this framework is powerful to perform generative reconstruction of the hidden patterns from the trained teachers and use it to train another replicate model. So that is the whole security aspect, right? First thing, you are stealing the data. It may have a lot of privacy breached, many more sensitive information has been extracted. And not only that, now we are using it to train another replica model, right? You see, it's a bigger damage. It is stealing of intellectual property. Okay, so this security, I'm showing the attack side. How can we safeguard? Okay, it's a different ball game. Okay, people started with a very simple looking approaches like, how can I can only let's say if the teacher is given to you, there is nothing. If I have access to the teacher, as I said, the deployment one where the teacher is given to you, the trained model is given to you, there is no safeguarding there, because because you have given everything about the parameters and the model architecture, everything is there except the training data. Okay, so here there is no safeguarding because everything is given to the attacker, or rather a dishonest user. Okay, so this is where we also explored further. We wanted to understand uh, how arbitrary data can be used as a transfer set. See, the whole point here is I am generating data that is close to training data. So some of us can ask the question, why does it need to be closer to the training data? Why can't we use any arbitrary data? Let's say I have some data I collected. It may be closer to the training data. It may not be closer to the training data. It's a natural question, right? why can't we use this? How will this data that I have will perform in creating a replica model? Do we need that transfer set always closer to be the real data or the original data over which the teacher was trained? So this question we asked in our 2021 WACV paper. So we say non-trivial performance is possible from arbitrary data also, provided if they are class balanced. For example, you say you collected data, but all of the data falls only in a subset of classes. Let's say there are 1,000 classes for the teacher. All the data that you collected covers only 200 classes, but the rest 800 is not covered. Then it may not be very useful. Okay, so you can collect the arbitrary data as long as it is class balanced. I mean to say it should cover all classes more or less in equal proportion. Then it will do wonders. So that is what we found in our WACV 2021 paper. So this is where I'll briefly cover it. It's not very important to focus at this point in time. But the story is that you can use arbitrary data, but class balanced. As long as the data set you're using, the transfer set uh, should have samples that get classified as all the classes. Okay, all right. The weak emphasis on realistic reconstructions. Okay, so this is something that is worth mentioning. So two approaches that we talked about so far aim to reconstruct realistic transfer set. Okay, still a big gap exists because it's not that easy to reconstruct realistic samples because the classification has a lot of unimportant data which gets discarded. For example, talk about CNN. CNN will have max pooling layer, CNN will have vectorization layer, right? All of that is to retain only the required information and shred out all the less important information. So that is a challenge. We cannot reconstruct what is lost. Whatever is important, whatever is carried forward to the classification, only that much we can reconstruct, right? We cannot have all the background information, all the other foreground that is not class specific. All is gone. All of that is gone because it has to build invariance to that noise. Why am I saying noise? Anything that is not a classification important is a noise, right? Only the patterns that are correlated to the label are important. That is the signal. Everything else is noise. Okay. Because of that invariance, because the model learned to ignore whatever apart from the class information, that cannot be reconstructed. That is the challenge in bringing out realistic reconstructions. It will not happen, right? Because of that, there is a still gap. Okay, then why not letting that go and focus more on the transfer? Okay, so that is where people modified the generative reconstruction. Let us not look for reconstruction that is realistic. Okay, let us do one thing. Let us make it truly adversarial. What do I mean by that? The teacher student pair penalizes the G when, let me show that the diagram and explain it. Okay, so where is the diagram? Just one second. Here. So when we started, we wanted to extract patterns that are closer to the real data which is not available to us, right? The training data which is not available to us. So people said, okay, let us not carry that notion. As I said, it is impossible for us to reconstruct fully because all the lost information is lost forever, right? So that is why people say, okay, so whatever I'm generating, I'll try to generate where my student and teacher disagree. Okay, so wherever my teacher and student disagree, that is what I want to generate. What is the benefit? Now I'll take that and I train my student to imitate my teacher. Okay, I want my student to imitate everywhere in the space, not just only on the real looking samples, right? It is a restriction. What I'm generating is real looking samples. My student will imitate the teacher only there. But I'm sure that what I'm generating is not as close to real data as possible. It will be impossible. So Why am I training my student to imitate my teacher only in a limited setting? That too, I am sure this is not actually real data. Real data is somewhere there. I am not going there. So why do I want my teacher and student to agree here? I want my teacher and student to agree everywhere, so that we are not restricting the distillation to be only on the synthetic data. So again, I hope I conveyed it clear. So because we are not able to generate real data, I want my teacher and student to agree everywhere. So that is why purposefully you generate data where teacher and student are disagreeing and use it to agree. Okay, so this is called adversarial exploration, because you are adversarially exploring where the student is not doing or imitating as a teacher. Then you identify, generate samples, and train them to agree. Okay, it is like student chasing the teacher everywhere. Just imagine a 2D space. Okay, a 2D space is simple. All your data is two-dimensional data. So you start from, let's say, 0 0. There the student agrees with the teacher, but you encourage the generator, you go find some other place where the student and teacher are not agreeing. So the generator goes there. Then you feed that data and train your student to imitate the teacher. And you do this again and again and again, so that you try to cover as much space in the 2D as possible. Only difference is that you are doing in a high dimensions. What is the dimension? The dimension of the image, W by H by 3. In that dimension, imagine a very big space where your generator is giving samples from there, trying the student to imitate the teacher, and then goes to somewhere else, bring those samples, goes to somewhere else, bring those samples. Everywhere in that space, now the student imitates the teacher. It is called curriculum learning, because slowly easy sample fed, that is where student easily imitates the teacher. Now it goes to slightly difficult, a little more difficult, a little more difficult, etc., etc. Everywhere the student now follows the teacher. Now we don't worry about how they are looking. We just want the student to imitate the teacher. This is also clever. I feel I clearly remember this paper when I read in 2021 in Edinburgh. Yeah, that is around 2020-21. I was impressed with this idea. This is called adversarial exploration. Incidentally, I read this paper. This paper was from the Edinburgh group, machine learning group only. So I like this. So this is called zero shot knowledge transfer, but adversarial belief matching, because they adversarially fed the data where the student is not imitating the teacher. They found all those samples and then fed it to student to imitate. Right? This is what happened. And later works followed this ideology, this framework of adversarial exploration, so that you don't worry about the synthetic data to be real, to be close to the training data. We don't really care. All that we care is everywhere in that space, student should match the teacher. Now, somewhere in that space, real data also falls. So your job is done. You're solving a bigger problem. Everywhere in the space, the teacher, student imitates the teacher. Somewhere the real data has to fall. So you are done. Okay, but it is a little challenging. It is you are solving a difficult problem, because we have to do this because you don't have the training data, you cannot access it. So you are ready to whatever training data it was. Okay, so this is why the samples that are generated were no way closer to real data, but the performance of these samples, uh, training the student was really good. Remember, once we train the student on this data, we will evaluate on the real data itself. The generalization performance has to be compared on the real test data, not on this data. Okay, for experimental purposes, we use real test data only. But during the training, we will never use any training, the real data. All this kind of uh, meaningless synthetic data will be used to transfer knowledge from teacher to student. Okay, so adversarial exploration, DFAD 2020, it investigates for better discrepancy measure, extends the DFKD to semantic segmentation. Lot of stuff happened. All that I explored or all that I discussed so far is only for classification setting. Simple, straightforward. But people applied this kind of model stealing, data stealing to semantic segmentation and other computer vision tasks also. Please understand that although I'm focusing on object recognition task, it is far beyond computer vision. It goes to LLMs, NLP problems also. Towards the end, I will show some, I will briefly mention some of the works that are extended versions of these on foundation models. Okay, but I want you to appreciate and understand these early works that kind of showed the security aspects in AI. Okay, particularly in computer vision, but it goes beyond computer vision. Okay, right. As I said, it is possible to do a lot of stuff. Adaptation, continual learning. People showed this in computer object detection also. When you have an object detector like YOLO, no training data is given, but YOLO models are ready to be downloaded. You can just create a replica of that without training data. What am I getting? I'm compressing the data to be deployed in a handheld or resource restricted device that is not to be licensed to anybody but you, because you are using an open source model. You don't need to pay them, you don't need to do anything. It is kind of owning a replica of that model, which can be deployed onto some resource restricted environments. Remember, this is only one setting. What we discussed so far is a model which is given to you, the deployment scenario where you are getting the model in your hands. Okay, now this is called white box setting. Why do I call it white box setting? Because everything is accessible, fully accessible. The model is in your hands. You know the parameters, you know the architecture, you know the output classes, everything. Okay, it assumes complete access. That's why we started with model 1, where the fully trained model is given to you. Okay, everything, softmax predictions, gradients, everything are given to you. That is why you can access, you can generate, um, you can train the generative reconstruction or noise optimization, everything. But DL models are valuable. It involves data collection, labeling, maintaining them in servers, model architecture, design and training. A lot of expertise is there, right? So these are considered intellectual properties. They need protection. So people consider wherever possible deploying it in cloud and making it accessible via paper query. Okay, so this is how you need to understand machine learning as a service. You have collected a lot of data as a service provider. You used intelligence, you recruited researchers that worked on model training, model designing, and all that. You have a model in the end, and you created an API so that this provides access to different users, variety of users like mobile users, enterprise users, etc., etc. Okay, so via this API, you provide access to this model. Okay, so that model is where your business is, right? This, you have to imagine this as a ML as a service, just like any other cloud-based service. Okay, now this is where the problem comes. How the model extraction attack happens in ML as a service setting. Let's say this is the person who put in hard efforts and performed the training and created the model F. Now, some dishonest user performs, he or she will hide as an honest user and perform some queries X and receives the responses from model f of X. Now this is where they may venture into creating f hat, right? But what do we have here? Do we have complete access to the model? No. Do we know internal architecture, parameters? Nothing. We simply know f of X for all our X, not any X. Whatever X we input, for those X only we know f of X, right? Because for every X we are inputting, we are paying. It is costly. We can't just dump unlimited X. For every X you are paying, because this is a service, right? So you have to be really clever and careful in selecting those X's for which you need f of x. Okay, so in practice we will say only 400 queries are allowed. Can you create a replica of that X? Right now, imagine a security breach scenario, or an attack where you are creating f hat, a replica of f, with a budget of 400, 500 queries only, because each but one query means some money, right? So for every given budget there are a fixed number of, or a maximum number of queries that are possible. Now in this setting, how do we go about? Okay, so this model has, this setting has no access to the model. We don't know what family it is. We don't know whether it is a CNN. We don't know whether it is a SVM. We don't know whether it is a BIT. We don't know the parameters. We may not be able to access the gradients. The final output also, we don't know whether it is correct softmax or incorrect softmax. We don't even know how many classes it was classifying, right? It will just give top 3 labels or top 4 labels. So you click a photo on the road, you click a photo of some object and upload it to the cloud, and it will say this object can be one of these three in the same order: top 1 label, top 2 label, top 3 label. You don't know how many labels it is predicting: 1000, 100, 2000, we don't know, right? This is a very complex situation compared to what we discussed. In this scenario, how do we replicate f of f hat of x? Okay, that is why this is called black box setting. Okay, so because it is very clear why we call it black box, because nothing inside the model is visible to us. We cannot make any sense of the internals of the model. Just to put everything in context, just to make you appreciate the problem, I'll take a very simple example. Okay, let's consider a linear regression. So one of the very simple machine learning models. We almost start with linear regression in almost every course in machine learning. Okay, now the hypothesis class here is regression model from RD to R. Okay, in simple terms, we are building a model which converts RD input to R, a real quantity. Okay, d-dimensional input becomes one real scalar. A linear regression model is converting that. How do we represent it mathematically? It is how we represent it mathematically. A0, this is the bias term, constant term. A constant in the sense it is also learnable, but it won't interact with the d of the features. For every d of the d parameters, there is a coefficient ai, xi. I runs from 1 to d. This is your model, linear regression model. Simple, straightforward. Now, for every x, you will get f of x, right? Now, I'll give a question. Okay, please bear with me and try to answer this so that it becomes a little engaging experience for both of us. Now, you tell me, I ask you to estimate the parameters A0, A1, and so on, AD. Total D plus 1 parameters are there. Now tell me how many queries you need to make to this model so that you can extract A0, A1, and so on, AD. Okay, the problem is clear. I told you the model you are accessing over cloud is a linear regression model with d-dimensional input to a scalar output. If you give a d-dimensional input, the model will predict a scalar and give it to you. Now your objective is to steal this model, means estimate the parameters A0, A1, and so on, AD. Now the question is how many queries you have to make in order to estimate these A0, A1, AD accurately. Anybody? Any answers? I'll give a hint. It is estimating the parameters A0, A1 when you know the output and the inputs. Okay. Try to recollect the linear algebra. This is just a bunch of linear equations. It's a system of linear equations. Now I'm asking how many equations are to be there for you to estimate the parameters A0 to AD. So if there are n parameters, D plus 1, yes. Ahana Mahapatra, correct. Because essentially each equation has D plus 1 parameters. If there are D plus 1 equations, it will simply form a system with D plus 1 equations and D plus 1 unknowns, right? You just need only D plus 1 parameters to estimate, right? You can substitute your X in each equation and it will become a system of equations in A0, A1, A2 and so on, AD plus AD. If I start with 0, it will be AD. Okay, so with D plus 1 equations, you can solve a system of linear equations and bingo, you have the uh, system stolen, right? But it is not that simple because we generally don't know what is that system. People who are selling the model, you can know where, I mean, briefly and broadly. For example, if you are buying a system, if you are buying a cloud based service, you will try to understand, is it really worth it? You want to understand, if not the exact technology, you want to understand what went there, right? So to that extent, some people may know. Even the seller has to reveal, right? They have not much but some information to sell it well, right? For example, nowadays everybody labels their model as their work as AI driven, some deep learning models or something will be there, right? So that kind of information only is available, not this full information that it is a regression model, linear regression model. All of that people won't say. But I'm just giving you a simple scenario. Even in the parameter less scenario, you can try to steal model with some assumptions. Okay. An adversary queries these x1, x2, and so on, xd plus 1 that are linearly independent, so that you will solve A inverse times F will give me, sorry, X inverse times F will give me the A. Okay. So we can solve the linear system of equations that way. But the problem is, in black box setting, you may not have that kind of information. But there are works. I'm not getting into the details. They're a little more involved. The point to be taken at this point in time is, even with deep neural networks, with so much nonlinearity, with so much unknowns, like you don't know the family of architectures. Is it a ResNet family, VGG family, GoogleNet family, VIT family? With all that unknown things, also it is possible to extract some information. So adversarial exploration makes the model susceptible and leaks some information that is valuable. Okay, again, I am not really getting into those details. Okay, let me give a very broad detail. Let's say we don't know what is this victim model. Okay, somebody deployed this victim model. It can be VIT, it can be VGG, something. Black box access only. What is that black box access? You generate X and put as input, and you will get the output. Right? Output is basically the top label or top K labels, not even full softmax vector, only top K labels. We don't know what is the full number of labels also. Okay, so you try to create a replica. Replica means with only those possible um, output. You try to train a neural network in your own lab. Okay, so there are different ways to create such a replica. In the adversarial setting only, you try to minimize the loss between the victim's predictions and the student predictions. Okay, because this is not known, we cannot backpropagate. This gradient approximation has to be done. We cannot really backpropagate, but here we are training our own students, so we know the full details and you can backpropagate. Okay, so when you don't know, we can do some approximations to gradient backpropagation and try to get the student to do as well as the victim. Okay, so this surrogate model, we call it surrogate model, will be trained in your own lab, and that will be used to create the synthetic data and train simultaneously. Okay, again, I'm not getting into the math. So it requires softmax output of the victim sometimes. Sometimes you can manipulate to some approximation that softmax also. Okay, I would not say approximation, but you have to take a filler for the remaining thing. Okay, right. So black box model in model extraction or knowledge extraction in black box setting also, essentially it is victims stealing the victim or creating a replica of the victim. Okay, so it gives, to safeguard, these days people are only giving top one label but not the softmax. Some of them give softmax but purposefully give inaccurate second, third, fourth labels. They will only maintain the correct top one, but 2, 3, 4, 5 labels that will be purposefully inaccurate because God knows who is creating a replica. If we give all the correct 1, 2, 3, 4, 5 labels, they may be able to get accurate replica. But if you on purpose give 2, 3, 4, 5 labels, you are not disappointing the honest customer. At the same time, you are challenging the dishonest customer who's trying to create a replica. Okay, so that is a very bare minimum, very simple defense people follow. Okay, so in hard label setting also, people try to create replicas for victim. They call it surrogate or clone model. Somehow they try to approximate the behavior of the victim model as much as possible and try to do the same generative reconstruction. Okay, the generative reconstruction where we try to adversarially match the clone model, right? So the only thing is that we don't have the victim model. How do we create a clone model for training? This purple box is where different papers vary across the literature. Okay, all right. So again, I'm not really hoping to take you to all those mathematical details. All the links are available. You can also take a look at. Okay. All right. So I want you to take the bigger picture away. Okay. Model extraction shares similarity with active learning. Okay. Active learning is basically you choose what to input, what to train your model on. Okay. Because active learning assumes that you don't have labels for all the training data. So because labeling is costly, you want to understand what samples need to be labeled and used for training. Okay, this also is very similar, right? An attacker is choosing the input to get f of x so that he can create a replica. So it is very similar. Active learning essentially is a genuine problem where, because some cases labeling is difficult and cumbersome, right? For example, think of semantic segmentation, depth estimation. For every pixel in the image, you want to assign a label. It is very challenging. Lot of man hours will go into creating the labels. So that is why in problems like that, people understand what samples need to be labeled. Not all need to be labeled or can be labeled. So can we identify those vital samples for labeling? Here also, model stealing also very similar. The dishonest user has to identify, because it is costly to run extraction, run model inference on all the data. They will select carefully what needs to be input to get the output so that they can create a replica. Okay. So every research in active learning can be converted into an attack. So that is what I want to say. Okay, active learning research can become an attack. Okay, right. So there are a lot of attacks. Membership inference attack. What does it mean? What does it mean? Identifying whether a sample was part of the training or not. Right. So if I am not wrong, there was an attack on AIMS servers where the health records of some of our policymakers, the MPs and ministers from Delhi was there. Okay, so again, we don't know how sensitive was it, what happened, etc., etc. But we could not estimate the extent of damage. Okay, whenever an attack happens, we really cannot know comprehensively the extent of the damage, right? It looks like a simple access, but you really don't know, okay, until it manifests in a big way. Okay, so membership inference attack is basically trying to understand whether this particular sample was part of the training or not. Okay, model inversion is, as I said, the model inversion is extracting the training data. That is what we have done, right? Extracting the training data, patterns in this case. Model extraction is creating the model replica, duplicate model, or replica model that we just created, the student that we created, right? So many such attacks are possible, which are dangerous, which need to be protected. Okay. Again, I'm not getting into the details. Right. What next? So this is where I want you to think. I want you to imagine even the worst things that are possible. Efficient and effective reconstruction, because as I said, the methods that we discussed are computationally involved. Lot of iterations of noise optimization. Generative reconstruction means a generated architecture has to be trained. Okay, all that is fine. Beyond that, now we are into foundational models era. We are not training one model for each task. We have a big foundation model. We try to fine tune or use as is that model across multiple tasks. How can we imagine attacks on such foundation models? What are the possible attacks on those uh, foundation models? That is what we need to understand. Just 1 second, I'll come back. Just 1 second. Somehow I lost the screen. Is the screen visible? Can somebody tell me? Okay. I think I'm back. Right? Can everybody see? Can everybody see the screen? Okay, let me check here. Yes. Okay. Okay. Cool. Cool. Something disturbed me. Okay. Fine. So this is where we are heading actually. So what happens even in the foundational models era? Do you think the models are susceptible? Do you think these attacks can be adapted to foundational models? Yes, the simple straightforward answer is yes. So some of the recent works that are on the foundation models, I have it on the screen. Again, I'm not getting into the details. I just want to carry the foundations of this attack, and I want you to be aware of the security aspects that are surrounding the AI. I know I'm covering only one half, which is the security of AI, not AI for security. Okay. Anyway, so this is very important for us to understand what sort of attacks are possible. And for example, you see here model leaching and extraction attack targeting LLMs and stealing part of a production language model. Okay, this also is very interesting work. I hope you will get time to go through them later after the program is over. So yes, in short, what I'm heading you or hinting you is that even the foundation models, despite their complexity, despite their ML as a service nature, it is possible to launch and create security aspects. Okay, and I want you to understand the difference, the broad difference between the classical model and the foundation model in this scenario, in the security scenario. For example, output in the classical scenario is just a label or a probability vector where softmax output is given. But in foundation models, generally you see output may be a bunch of tokens or embeddings or trajectories. So you need to differentiate and understand the architectural difference. Okay. Usually on the classical side, usually it targets one predefined task because the classical way of developing models was one model for each task. But here, foundation models means they simultaneously can solve multiple tasks. So we may have to target generality or selected emergent capabilities of that foundation model. And people try to look at it this way. And this will give rise to possibility of attacks. Okay. And look at surrogate model. Surrogate, we just discussed that it can be trained from scratch. But in foundation model scenario, surrogate usually starts from another pre-trained foundation model, wherein deep learning made models as a commodity. What I mean by that, people who train models can upload and make it public, right? So we don't need to start anything from scratch. You can identify the most relevant model that is publicly available and start from there, right? That's why I say deep learning made the models a commodity, right? So this happened right from the ImageNet days, 2012, 2011 onwards, right? So because of that, it is easier to launch attacks also. Okay. Again, some more differences, often independent queries versus multi-turn and adaptive query. Because foundation model, you can slowly make it a conversation with it and then try to extract information that is sensitive. And you can do wonders. As I said, there is no limit about what you can do, right? But in classical setting where you simply put a query and get f of x, but here you can run conversations, you can have a prolonged interaction with it to extract, to win the trust also. For sometimes, for example, jailbreaking and all, right? You can uh, put in the convincing prompts to make it do what you want to do, beyond the guardrails. So all of those things you need to be considered, but there can be security issues that are more dangerous in foundation model era than the classical, because the very ability of these foundation models to do multiple tasks simultaneously may also become their vulnerability. See, that is what I want to say, right? They are smart, no doubt about it. They are equally vulnerable is what I want you to suspect them to be. Okay, all right. So in the interest of time, let me just give away three important conclusions to you. Okay, so there are a lot of AI developers, lot of AI researchers. I believe the competitive advantage may shift from people who owns the most capable model to people who can control what that model is allowed to access, allowed to remember, allowed to do. Okay, if you are the person, if you are the organization who have the best control on what the model is allowed to access, allowed to remember, allowed to do. Okay, if you have best control, like you 100% know and control what the model is allowed to access and remember, then there is no way you somebody can take out something sensitive, because you are controlling. If you feel it is possible to be leaked, you don't allow the model to remember it, right? If it is possible for somebody to access, you control it already, right? That is, I believe, is going to be the future. Not developing intelligent model, but developing a model where you have the control. Okay, it may look like handicapping the model, yes, but that is what we need. Okay, right. Just think about it. Okay, these are my raw thoughts. I just wanted to give you some for chewing on. Okay, now another thing I want to say. The first major AI-driven cyber catastrophe may not be caused by a rogue superintelligence. I believe it may be caused by a very, very ordinary, well-aligned, not malicious AI assistant, which is given the legitimate credentials, which is connected to those sensitive systems that need to be protected, which is manipulated by some malicious intent, manipulated by, let's say, some untrusted email or a document which has been poisoned, because you can incorporate prompts also in documents these days, right? And which is permitted to act without adequate supervision, right? I feel you don't need a super intelligent malicious rogue agent. All that you need is a very, you know very well designed, well aligned means which follows all the protocols carefully. Okay, but a simple system which is connected to sensitive information which can be manipulated by an untrusted system, like a document or an email, which is permitted to act without adequate supervision. See, that is what we are heading, right? Why is that everybody want AI agents to run the show? That is where we are losing supervision. You are giving full freedom. You just get it done. You work with multiple agents. You just get it done. So that is where I think we are losing control. That is where more and more security aspects are coming towards us. Okay. And as I said, the question now may not be how do we make AI intelligent enough to defend us? That is definitely a good question, but that may not be our immediate focus. I feel how do we ensure that an intelligent system never acquires more authority than our security architecture can safely contain? Okay, so again, spend a minute. Generally, what people we look for is how do we make AI intelligent enough to defend us? Maybe we should look for how to build an intelligent system which never acquires more authority in the first place than our security architecture can safely contain. What I mean by that is it is allowed to acquire more authority to break the security. Okay, so this is where again these are very I spend a lot of time. I got to know about this thing yesterday evening, so I kept thinking about what could be some good um, concluding remarks for this session. I came up with this thing. Please chew on them. Okay, so I think we need security aspect to be considered by default. See, in the initial days, we considered only about the performance. All that we need is the best performing AI. Then slowly we said, no, 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 performance alone is not sufficient. We need explainability. We need them to be transparent. We need them to talk to us, explain to us how they reached that inference. Now I say another desiderata, another requirement about security is very much there already. We need systems that behave like this, as I said, right? Not just the performance, not just the explainability, but safety compliant, security compliant, privacy compliant. Okay, so I think with that I will stop here, and I thank the organizers very much for giving me this wonderful opportunity. And if you have any quick questions, I can take one or two questions.
Participants may ask any question on your chat box.
Right. So on my side, I will try to share this the slides. If that is helpful, you can collect it from the organizers. I will provide that to Dr. Ramesh Garu.
Thank you very much, sir. Thank you very much for your support. Huh?
No problem. Yes. Yes. Once again, I'm very.
Thank you very much, sir, for giving a wonderful session. So, in this session, he explained about how the adversarial framework for DFKD is doing on, and then he also explained about the model reconstruction attack, and then in model reconstruction attack, he explained some noise optimization. In noise optimization, he explained that he explained the computation power is more expensive. Then he explained about the generative deconstruction. Under that, he explained the GAN model, and within this GAN model, he explored the non-trivial performance providing class imbalance programs. Then he also emphasized the realistic deconstruction models, and he explored the adversarial p-like matching using ZSKT. And he also explained about machine learning as a service using the black box testing and extracting the linear regression models. So thank you very much for giving a wonderful session for us. Thank you very much, sir.
No, the pleasure is all mine. There is one question from Mr. Satyam. Students who starting research in security, what he should start from? It's a very good question. Security, unfortunately, we do not have enough programs. For example, cybersecurity is something where most of the IITs do not have not just IITs, the other universities also, we do not have proper programs to start with. So that is exactly where IIT Hyderabad also thought about and started a program, IITH Cyber AI. So this is something we recently started, certificate program in AI and cybersecurity. But only one batch passed out. We are working on the second batch. We're working on the curriculum. Soon we may be able to bring it back. Please stay tuned. Okay, coming back to the question, it's not straightforward, Mr. Satyam. Unfortunately, we have to have both sides, AI and security. We need what is security, how do one think about security, at the same time what is AI, how do we use AI for security, and what is the vulnerability of AI towards security. Both of them have to be co-studied. Okay, the simple answer is, at a master's level, maybe we can pick some programs where both of them are together. Or if you just worried about only security, there are master's programs. For example, IIT Hyderabad CS also has a master's specialization where we call it NIS, Network Information Security. It's a specialization, master's level only. So BTech CS people, other people, other specializations also can do it. You should look for programs like that. Only at master's level they are there. There may be a lot of other certificate programs also. You try to study them, what is the requirement, what is the content, and accordingly we can plan. I'm not aware of, unfortunately, any other public resources like NPTEL Swayam or Coursera. There may be some, just that I'm not aware of, unfortunately. I'm sorry. Does it answer your question, Satyam?
Thank you, sir.
Okay, thank you. Thanks
For
very
this
much.
wonderful session. So now, dear participants, we are taking 5 minutes break and then come back again.
All right, I'll leave the call. Thanks.
Thank you, sir.
Thank you very much. Once again, thanks, Andy. Thank you very much, Ramesh Garu and others who are organizing this.